Um, okay, so let me start by introducing myself. My name is Evren Sirin. I'm a co-founder and the chief scientist of Stardog. I've been working on knowledge graphs and semantic technologies since early 2000s and participated in the standardization efforts for these technologies over the years as well. So today in this training, I will talk about how to map relational data to RDF graphs. The RDF specification developed by W3C is a mapping language for doing this. We'll start with discussing what conceptual mapping is and then go over the syntax of the mappings and see how we can query data stored in a relational system using Sparkle. At the end, I will briefly discuss how to map NoSQL data sources like MongoDB and Cassandra into RDF as well. So before we get into the technical details, I'll spend just a few minutes to give you a high-level motivation for virtual graphs. I'll talk about the mappings, show a demo of how to use those mappings. At the end, I'll try to answer as many questions as possible. So for the motivation, I'd like to talk about what we think is the most important problem knowledge graphs address, the data side of problem in the enterprise. As most of you know, organizations have been built to manage data by department and type. These data sources are disconnected from each other and can be used within the context of the department or the application that generated them. But most strategic questions in the enterprise can be answered only when you have a unified view over all the different data sources. And that's where we can use virtual graphs to connect data from multiple sources without moving or copying it. So a virtual graph exposes structured or semi-structured data as a graph using declarative mappings while leaving the data in place. And when all the data sources of interest are represented in our knowledge graph, we can easily connect nodes from different sources and create a unified view over all the data. In Stardog, we use this kind of unified view to connect the data sources and then provide tasks like business analytics, machine learning, and more over the knowledge graph. At this point, let me mention that the material that I will cover today, all the data files, mappings, queries are available. You can go to the tutorials page on our website for the details of virtual graphs and RDF, Sparkle, and other features of Stardog as well. And there's a GitHub repository linked from the tutorials where you can find the actual data files. So in this webinar, we are assuming that you are familiar with the basics of the RDF model. If not, you can go check out the tutorials page that I mentioned. But I'll quickly do a recap of the RDF terminology, at least to refresh your memory. So RDF has a special vocabulary to refer to the nodes and the edges in a graph. An edge is called a triple because it has 3 components. The source node of the edge is called the subject. The target node is called the object, and then the edge identifier for the relationship between those 2 nodes is called the predicate. So the identifiers used for predicates are called properties. So in this example, member is a property that's used in the predicate position of the triple we see here. And an RDF graph is defined to be a set of triples which can be visualized as nodes and edges, as we see here. Okay, there are 3 different kinds of RDF terms. There are IRIs, which are nodes that have unique identifiers. IRIs are also used to identify the predicates as well. The nodes that represent primitive values like numbers and dates are called literals. And there are also blank nodes, which are nodes without an explicit identifier. But we won't talk about them too much today. Okay, so we'll have a running example in this webinar, which is inspired by the Open Music Encyclopedia MusicBrainz. MusicBrainz collects and stores music metadata in a relational database and makes it available to the public. The database schema for MusicBrainz is quite complex and not suitable for this webinar. So we are going to use this simplified schema that we see here. But if you are interested in more complex examples, there's actually an open source project called LinkedBrainz that provides the complete mappings for the MusicBrainz database. So you can find that link in the tutorials page as well. So in this simplified schema that we are looking at, we have one table for artists, one table for the albums that the artist released, and there's another table for songs, the tracks in those albums. Tables have columns for attributes such as names and descriptions. And there are also some foreign key constraints as shown by the lines connecting the tables in the schema. So looking at this diagram, it's kind of obvious that the schema is conceptually representing a graph, and the foreign key constraints are hinting us what kind of connections we have in the graph. And in the R2RML specification, there's actually a description of how you can take a relational schema like this and automatically create a mappings for a default RDF schema based on the primary and foreign key definitions in the schema. And this default mappings might be an easy way to get started, but most of the time we want to map the relational schema to an existing RDF schema, a schema that we developed to represent our domain. So in this slide, we are looking at a simplified visualization of an RDF schema for representing the music data, where you can see the similar artist, album, song concepts as in the relational schema. We'll see the details of the schema as we look at the mappings in more detail. So I'm not going to talk about this too much right now. Okay, so we'll first look at kind of the intuition behind the mappings with a graphical example before getting into the syntax of the mappings language. And generally in the relational model, each table represents one entity type, and rows of the table represent instances of that type. For example, here you see the artist table on the right side of the slide, where the rows are representing different instances of artists. So when we map a table to RDF, typically there's an RDFS class corresponding to the table that we are mapping. In the artist table, we actually have two different types. So we have both solo artists, John Lennon, Paul McCartney, also bands like the Beatles. And the type column is differentiating these different types. But for now, let's kind of ignore that column and just simply assume we'll use the artist class for all the rows. Again, typically in the mappings, there's a RDF property corresponding to each column, and the values of the row become nodes linked to the entity node using that property. So we have the name column in the artist table. It would become a node in the graph. And again, usually the columns that are associated with a foreign key would become IRIs, and other columns would be mapped to literal nodes. So in this case, the name column would be mapped to a string literal in the RDF graph. And the artist node is an IRI, which is constructed using an IRI template. So an IRI template is just like an IRI, but it includes variables that will be replaced with actual values. So the artist IRI template we have here concatenates the local name artist with the ID column of the artist table. So the names inside curly brackets identify the columns of the table. So when this template is instantiated with the values with the ID column, we would get IRIs like artist1, artist2, artist5. The colon at the beginning of the IRI indicates that the IRI belongs to the default namespace, which is not shown here. But we would get a fully valid IRI as a result of this template. And the combination of the namespace, the local name artist, and the primary key ID that we are using here ensures that the IRIs we generate will be globally unique, and it won't clash with the other IRIs we generate from other tables, or maybe the IRIs we might get from external data sources, other data sources. So we mapped the album table in a similar way with one node representing the album instance. Then the name and the release date columns are mapped to literals. And then there's the foreign key here, the artist column, which will be naturally turned into a link in the RDF graph. So for the artist column in the album table, we simply use the same IRI template that we used for artists when we mapped the artist table. So as a result, the both nodes created by these mappings will refer to the exact same node, and we will get the links between the nodes created by those two mappings. Okay, then we map the songs, and there's another foreign key reference here. But one difference with respect to this example is the track property in our RDF schema goes from albums to songs with respect to its direction. But here the track table will be generating the song nodes in our RDF model. So this will cause a difference when we are defining our mappings a little bit. And I'll highlight it when we are looking at the actual mappings. And one thing you'll notice here as we are creating all these mappings, the implicit graph structure in the relational model becomes explicit links between the nodes in the RDF graph. Okay, finally, we have the songwriter table, which is quite different than the other tables. Because the rows in this table does not represent an entity. So this is what's known as a junction table, which is a standard way to represent many-to-many relationships in a normalized relational schema. So sometimes they are also called bridge or associative tables as well. You might have heard those names. So in the songwriter table, each row is representing a link between a song and the artist who wrote the song. Of course, for simplicity, we are not differentiating like composer from lyricist and those kind of things. So we are just calling everyone a songwriter. And so if you look at the table here, there's the song identified by ID1, which is La Me Do. And there are two writers for this song, artists with ID 1 and 2, that corresponds to John Lennon and Paul McCartney. And so when we map a junction table like this to the graph, what happens is we get a single triple as a result of that mapping. So each row will generate one triple. So like the La Me Do song connected to John Lennon for the first row, and the song connected to Paul McCartney for the second row, and for all the other rows in the table as well. So this is pretty much all the intuition you need to know for these mappings. And what R2ML specification does is kind of formalizes how these mappings would be defined and how the templates, IRI templates are defined and the mappings for the primitive values and those kind of things. Of course, this is great to provide a clear semantics for these mappings mean and also allows interoperability if when you are exchanging mappings between different systems. So R2ML has some vocabulary to refer to the different parts of the mappings. So a triples map is the mapping from one row of a relational table or a SQL query to RDF triples. So what we were looking at with artist table was one triples map, album table was another triples map, and so on. Subject map defines the subject that's shared by all the triples generated from that triples map. So a triples map always has a single subject, and the subject map shows you like the IRI template, like the artist IRI template, album IRI templates that we have seen. And then the additional triples generated by the triples map are defined using what's called as predicate object maps. So basically defining the predicates between the subject and the other nodes that are being created and what predicates are used to connect those nodes. So this is how the R2ML syntax looks like for defining these mappings. So this is the mapping for the album table and kind of shows the same information that we were looking at in the diagrams before. So you have the input table or the query specified at the beginning, selecting all the rows from album table. Then there's a subject map specifying the IRI template for the subject, and then the different predicates that will be used to map the different columns. So like the foreign key artist column is mapped with an IRI template. So that becomes an IRI node. The other columns will become literal values, and the types of those literals will be determined by the SQL type of these columns. So the dates become SQL dates become XML schema dates used by RDF, like varchars become string literals and so on. So in Stardog, we provide a more concise way of writing these mappings that we call Stardog mapping syntax. And the syntax is kind of extends the Sparkle syntax, a little easier to write. But we also support automatically translating the mappings between the SMS syntax and R2ML. So you can kind of go between these two syntaxes. If you need to generate R2ML mappings, you can do it automatically by first writing SMS mappings and asking Stardog to export it in the R2ML syntax. And but one advantage of SMS that I'll briefly discuss at the end is you can use it to map non-relational data sources as well, which is not supported by the R2ML specification. Okay, so let's quickly go over these different parts of the SMS mappings. So at the top, we have an optional name that we can define for a mapping. It can be an anonymous mapping too, but you can provide the mapping name. Then there's the input table, which specifies the query that we will use to map to RDF. So in this case, we are again selecting all the rows from the album table. And then in the third part of the mapping, we have the output graph. So this is using Sparkle syntax, where variables are will be instantiated based on the values we get from the relational query and based on the value mappings defined in the next section. So in the where clause, we define these IRI templates. So the ID column, the ID values coming from the SQL query result will be turned into an IRI based on this template. And then we bind the resulting IRI into the album variable. And in the previous section, we see the album variable becomes the subject of these triples. So it's the same kind of information represented in RDF in a slightly different syntax. And now let's switch to Stardog Studio, which is the IDE we use for interacting with Stardog. So there's a Stardog server running in the background. And in the Studio IDE, I'll show you the complete mappings and then how we can actually use those mappings to run queries. So first we need to have a database in Stardog for us to run queries against. So I created a database here called webinar. It's an empty database. There are no triples in it because initially all the data will be coming from the relational data sources. And here I have already checked out the Stardog tutorials GitHub repo. So this is the files you'll get from that repo. And there's okay, first of all, of course, we need to have the relational database for us to map to RDF. So here you'll find the SQL schema, the SQL commands that you can run to create the tables that corresponds to the example we were looking at. So the artist album table. There's also a membership table that I didn't mention explicitly before. So this is a junction table, just like the songwriter, which is linking solo artists to the bands that they are members of. And again, this is a very simplified example. Normally, we would differentiate between like past members of a band and current members. So we would track start and end times separately, but we are not doing any of that here. Okay, so this, you can run this in your relational system of choice, or the syntax you might need to change a little bit based on whatever system you are using. In this example, I have a MySQL database where this schema has been created. There's also another SQL file for populating these tables with just a couple rows for us to experiment with the mappings. So when you run these two things in your relational system, you'll get the tables with some data in it. Okay, we also have the mappings for all the tables written in the Stardog mapping syntax. So let's go over these all the mappings here just to understand what's going on. First, we have the album mapping here, which is the example we were looking at before. Then comes the mapping for the artist table. And as I mentioned, the artist table has the type column, which means and solo artists and bands have different values for that type column. So in our mappings, we want to map the corresponding artist with a different type on the RDF side. So one way to do this is have a mapping to map the generic properties of the artist table, like the name and description. This is same for solo artists and bands. So we can simply get all the artists and then map those two columns in one mapping. And then we have another mapping where the input query now defines a restriction to say only return the artist rows where the type column is 1. And then in our RDF mapping, we say these nodes generated from these rows will have the type solo artist. And then in the next mapping, we change the query to restrict the type column to value 2, and then associate those nodes with the band type. There are different ways to write these mappings. So instead of writing separate mappings, we could have written a more complex SQL query that would map these integer values for types to the solo artist and band types, for example. That would be another possibility. But yeah, in this example, we used simpler SQL queries to write the mapping. And so for the member mapping and also the songwriter mapping, these are the two junction tables we have in this example. So in both cases, we have a single triple generated from each row of these junction tables. So for the songwriter, it's linking the song to the writer and linking the bands to its members for the membership mapping. And for the song mapping, this looks slightly different from the other ones because now here we have both some triples with the song as the subject of the triples, with this one additional triple at the end where the subject is the album and the object is the song. So this was the direction thing I mentioned before. There's kind of a mismatch in how the relationships are described in the relational schema with respect to how the directions are defined in our RDF schema. So in the Stardog mapping syntax, we can just take this one table and map it to multiple subjects like this. This is one case where it's slightly different than R2RML because as I mentioned in R2RML, each triples map needs to have a unique subject. So we have the R2RML translation of these mappings. And if we look at these mappings, you'll see that there's a song mapping that correspond to the triples with the song subject. And then for the linking the songs to the albums, we create a different triples map in the R2RML syntax. But yeah, as I said, you can write your mappings in this Stardog mapping syntax, and the corresponding R2RML will be generated even if it needs to split some mappings into multiple triples maps. So this is how the complete mappings look like. By clicking this Create Virtual Graph button here, I can register these mappings with my Stardog server by providing some of the JDBC connection parameters and credentials. So I have already done that, and when you click that Create button, what happens is in this Virtual Graphs view, there will be a new entry. So there's a name we associated with the virtual graph. We call this the music virtual graph. And then the mappings are shown here. And using Stardog, you can make using Studio, you can make changes to these mappings if you wanna rename some of the properties, and then you can just save your changes to update the mappings. The configuration parameters for the JDBC connection is defined here as well. And once you have the mappings registered in Stardog, then you can run some queries against it. So we have some sample queries. I'll start with this example, which is retrieving the band with the name Beatles, finding the members of that band, and then the names of those members. So I will select our empty database webinar. And here in the Sparkle query, we are specifying that these patterns should be answered by the virtual graph named music. So typically in Sparkle, you can use a named graph in the graph clause that will correspond to the graph stored explicitly. But when you use the virtual graph keyword here and execute the query, so first of all, we see that we get the results from the relational system with the IRIs generated based on the template we have defined, like artists 1, 2, 3, 4. These are the members of the Beatles band, and the names for the artists have also been retrieved. So as you can see, when you write these queries and execute them, it's as if all the data is stored in RDF format. But what happens behind the scenes, and we can see this a little bit by looking at the plan generated by Stardog, you'll see that this query plan actually shows you the SQL query Stardog automatically generated based on your input query and the mappings you declared. So that's the kind of power of the declarative mappings. We can, looking at those mappings, we can reason about them and write these kind of queries that will retrieve the data we need from the relational system on demand. And we can use more complicated Sparkle features. For example, this query is getting all the albums, their dates, applying a Sparkle function to get the year component from those dates. Then grouping the albums by the year they were released in, and then counting how many albums exist in each year. And you'll notice that in this query, instead of the graph keyword, we are using the from keyword, which is another way in Sparkle to define the input named graph. So you can use the virtual graph IRI in either of those keywords. So when we run this query, we get the results again. So since we have only 3 albums that we populated our tables with, we get 1 album for each of these years. But again, when we look at the plan, you'll see that Stardog actually pushed all the work to the relational system. So the Sparkle year function was turned into the SQL year function. The SQL grouping was used. And at the end, we simply translated the results back to literals, IRIs, and the RDF representation. So in all these examples, all the data is coming from the SQL system, but we can add some data in our local database. For example, in this query, we are inserting data into Stardog to store the birth dates for each of the artists we have. So basically the members of the Beatles. And using the IRIs, that's gonna match with our IRI templates here. So now if we go look here, the triple count for the database increased to 4. And now we can write a query which will retrieve the members of the Beatles and their names using the previous query. But then outside the virtual graph scope, we also are retrieving the birth date for those members. So when we write this query, it's the results we have seen before, then the birth dates coming from the Stardog side. So again, if we quickly look at the plan, you'll see that there's a SQL component where we retrieve the results from the SQL, and Stardog will join that information with whatever local patterns it needs to answer. So of course, you can use the same kind of idea to have multiple queries to multiple different virtual graphs and combine them, or combine multiple virtual graphs with some information stored in Stardog. And also, so in this case, the queries are going to the relational system as we execute the Sparkle queries, but sometimes that might not be practical for quality of service restrictions on the relational side. Maybe we don't have access to run queries all the time. So in that case, you can simply write a Sparkle update query to copy the virtual graph into your local storage. So since we already have the mappings that describes how to convert the relational data into Stardog, into RDF format, we can write this simple copy query, and for the source graph, provide the virtual graph, and then the target, just the regular graph IRI. And if I just run this query, what will happen is now all the triples have been stored in Stardog directly. Now the triple count increased to 41. So like I can go back to one of these queries that we have seen before. Instead of the virtual graph, I can run it over the local graph. Of course, we get the same results, but now we are not going to the relational system. So based on your application requirements, you can kind of switch between this virtual queries versus materializing the data. Of course, if you materialize the data, then you need to have some kind of schedule to refresh it if the external data source is getting updated. So there are pros and cons to every approach. But again, the important part is the mappings are good for supporting both use cases. And finally, very quickly, let me mention how we can use the same idea to pull data from different non-relational sources like MongoDB, and we are now supporting Cassandra as well as a NoSQL data source. That feature will be is included in the 6.1 release. And here, the mappings looks very similar as before. The only difference is instead of a SQL query, we have a JSON template that shows what input we will be converting to RDF. So the JSON template here will be based on the structure of the data you are storing in MongoDB or Cassandra. But the general idea is same, so there are some variables in this template that will be used to populate the RDF nodes. And we also support using GraphQL as a way to describe the input JSON structure. So GraphQL is the query language developed by Facebook that's being used widely in many web applications for dealing with JSON data structures in a simple way. So you can use a GraphQL query to say these are the fields that I'm interested in from this data source, and then they will be mapped to the RDF graph based on the mapping you define. So what you see here is also, let me quickly mention, the JSON data structure doesn't have all the primitive values, like, for example, the date data type. So you can cast those values to the corresponding XML schema data types. So in the SQL side, this kind of happens automatically based on the SQL types. But this kind of casting is also possible if you want to change the data type that you will use for matching the columns to the literal values. Okay, so yeah, we covered lots of things about graphs. As I mentioned, we have more details in the tutorials and the files for you to try with. You can download Stardog, have a trial version, and use those mappings and data files to play with the mappings and explore other things that we didn't cover today.